My name's William. Let's do some math. This video is going to talk about the rational zeros theorem and the process that you would go through in order to identify the possible zeros or roots for a polynomial. It's a four-step process that you'll go through. The first step is to identify the max number of zeros that the polynomial could have. And you do this by looking at the degree of the polynomial. So if you had, for instance, an x cubed as the first term, that cube, or that 3, is what tells you you would have, at most, 3 zeros or roots for the polynomial. The second step is to determine how many of them are positive and how many of them are negative. And you would do that by using Descartes' rule of signs. I will show you an example of that in a minute, but essentially it means looking at the sign changes between the terms of a polynomial. And if there is a sign change, that indicates that there might be a root, because you can think of a sign change when you're looking at a polynomial, something like a cubic like this. You can think of the sign change referring to the change in direction of a polynomial. The third step is to create a list of possible rational zeros. And that is where the bulk of the work is going to be done here. That is the rational zeros theorem. After you have created a list, you need to identify which one is the actual root, or more than one roots, depending on how many there are in your polynomial. Create a list of possibilities. So these are the four steps that I'm about to walk you through an example with. But that is what you will do every time that you try to find the zeros of a polynomial using the rational zeros theorem. So, for an example, let's look at this equation. F of x is 2x cubed plus 11x squared minus 7x minus 6. The first step is to identify how many possible roots there could be. The power on the highest term is 3, so there are at most 3 possible roots. That just gives us an upper bound on the work that we're doing. Step 2 is to figure out how many of them are positive and how many of them are negative. Looking at the polynomial as given to us, the first term is positive. We move to the second one, it's still positive. We move to the third term, and then we have a sign change, so that's negative. Then we move to the last term, and that's also negative. Descartes' rule of signs says that because there is one sign change there, there is one positive root for this polynomial. And the second part of Descartes' rule of signs is to plug in a negative x into the polynomial and examine that for sign changes. Plugging in a negative x would look something like this. You're replacing all of the x's with a negative x instead, and then you would simplify the polynomial to see whether you have a change of terms. Only the odd-powered things are going to have a sign change from the original polynomial. By that I mean this will be 2x cubed, but negative compared to the other one that was positive. Anything with an even power, that even power is going to get rid of the negative sign that you tried to put in here. So this term is still 11x squared, which is not different from what it was before. Essentially, all of the odd-powered terms are changing signs. And then this is the equation that we look at to figure out how many possible negative roots there are. In this one, we start negative, and then we change to a positive, so there's one sign change. We go from positive to a positive, that's not a sign change, but this last one is from a positive to a negative. So I've got 2 sign changes for that negative thing. So there are 2 negative roots possible. It could be that we have altogether 3 real roots, and we'll hopefully find them. It is also possible that there are imaginary roots, though. Maybe there are no negative roots. There's just one positive and 0 negative. That's something we'll have to deal with later. This particular example won't have any imaginary roots. I'll show you some later that do, and we'll go through the process of finding them. But for this one, step 3 is to list the possible factors, or to list the possible roots by looking at a combination of factors. The rational zeros theorem says that we can look at this constant term at the end and the leading coefficient at the very beginning, the 6 and the 2, and we can build fractions out of those numbers. I want to put all of the factors of the constant term on top. So the factors of 6 are 1, 2, 3, and 6. And we'll put the factors of the leading coefficient on bottom. Factors of 2 are just 1 and 2. And I'm using this to build a list of possible rational zeros. So I will take a number from the top and a number from the bottom, and I'll create a fraction. So if I had 1 over 1, that's just a 1. I could have a 2 over a 1. That would be 2. I could have 2 over 2, but that's already a 1. I've accounted for that, so I don't need to do that one specifically. I could have a 3 over a 1 or a 3 over a 2. 3 over 1 is just a 3. 3 over 2 I'll write like that. That's 1.5. And then I could also have 6 over 1 or 6 over 2. 6 over 1 is just 6, but 6 over 2 is 3, and I already have that one, so I'm not going to write that again. Oh, I did forget 1 over 2, a half. Let me put that in my list here. I wasn't going through meticulously enough. So this here is a list of all the possible rational zeros. And it's important to remember that for a polynomial with integer coefficients, if there is a rational zero, it's going to be one of these from the list, and these numbers can be either positive or negative. But the polynomial doesn't necessarily have to have all rational zeros. It may not have any rational zeros. We know from Descartes' rule of sign that there is one positive one, but these two negative ones, they could be two imaginary roots instead, so they're not two real zeros. There could be 0 negative roots, and that's a problem you just have to deal with. But I am certain that there is one positive root, so let's try and find it. So how do you do that? The process of step 4, identifying the possible roots, involves either doing long division or plugging in or synthetic division. I prefer to go through my list and plug it into the formula. Remember that f of x is 2x cubed plus 11x squared minus 7x minus 6. So I will go through and I'll take each of these numbers and I'll plug it into the formula, because if f of 2 is 0, say, then I know that x equals 2 is a root. It's a 0 for this polynomial. And I just take the number and plug it into each of the x spots and see what I get. In this case, though, I'm pretty sure 2 is not a 0. Let's plug it in and try it. 2 times 2 cubed plus 11 times 2 squared minus 7 times 2 minus 6. Let's see, if I crunch these numbers, it would be 16 plus 11 times 4 minus 14 minus 6, and pretty sure that's 40. So f of 2 is not 0, so 2 is not actually a root. Let's try 1. I'm pretty sure that one is the root. So 2 times 1 cubed plus 11 times 1 squared minus 7 times 1 minus 6. This would be 2 plus 11 minus 7 minus 6. That is 0, so this is a root for the polynomial. And at this point, we have found one root. You could keep on checking, but it's possible that that's the only real 0. If the other ones are imaginary, it doesn't matter how many of these from that list that I try to put in, none of them are actually going to be the roots for the polynomial. So I need to be able to come up with a way of finding the other roots. What I've done by identifying this 1 as one of the roots is essentially factor that original polynomial into something times x minus 1. Because if 1 is a root, then x minus 1 is a factor. And I have factored it, or I can factor it out of the polynomial. I want to find out what is over here, though. And the process for doing that involves either long division or synthetic division. So synthetic division is what we're going to walk through here. You take the root, in this case 1, you put it in a box, and then you take the coefficients from the polynomial here, the 2 from the x cubed, the 11 from the x squared, the negative 7, and the negative 6. And I'm going to use them to come up with whatever should go in these parentheses here, the reduced polynomial. For synthetic division, you start by dropping that number down, the 2, and then you will multiply the 1 by that 2, put it here, and then you will add down here, 11 plus 2 is 13, and then you'll multiply 1 times 13, which is 13, I put it here, then you add down, you get a positive 6, take 1 times 6, put that one here, add down for the last column, and I get a 0, which is good. You should always get a 0 there, assuming that we actually have a root for the polynomial. These numbers in synthetic division here are telling you the coefficients for the reduced polynomial. So since I started with the 2x cubed before, this 2 is going to be the coefficient for an x squared. The 13 is going to be the coefficient for x, and the 6 will be the constant term. This is the thing that was in the blank here, the parentheses. It's the remaining factor after I had factored the original polynomial. And now you could do the rational zeros theorem again. You could take this 6 and this 2, and you could come up with a list of rational zeros that you want to check, and you could plug them in to see which of them will actually work, and then do synthetic division again. But hopefully you recognize this as a quadratic that you can factor, so we don't have to go back through and use the rational zeros theorem anymore. We have some other skills in order to factor this. And it should factor down to 2x plus 1 and x plus 6. And I'll just bring down this x minus 1. Essentially, this is the factored form of that original polynomial that we were working with, the 2x cubed plus 11x squared minus 7x minus 6. So this is helping us to identify what the roots are. So x is a negative half from this factor, a negative 6 from this factor, and a positive 1 from that factor. The positive 1 we found by doing the synthetic division, and these others we were fortunate enough to be able to use our knowledge of algebra and our math skills to just come up with them without having to do the rational zeros theorem again. And you'll notice, just like Descartes' rule of signs predicted, that we would have 1 positive and 2 negative roots, that's what we have. A negative 1/2 and a negative 6. Those are our 2 negative roots, and that's our 1 positive root. If the other roots had been imaginary, we would have got to this point where we have a quadratic, and we'd need to use the quadratic formula or some other ninja algebra to solve it in order to come up with the roots. Fortunately, this one wasn't so bad, but we can go through another example in a minute. Just click on the other video.